Just waiting for a few more people. Welcome to the St. John Center, the Royal Astronomical Society meeting. A couple of questions. Yes, I'm in black and white. Why? I don't know why. It was in color the last couple of talks I had, and this morning or just now, it's gone black and white. I hope that's just the camera, not everything else I got to do here. All right. For those new to Zoom, there's a few things. I'm getting I think there's a couple of questions like, how come I can't see myself? This is a webinar, not a Zoom meeting. In webinars, only the panelists are the ones you see. The people who are guests and participants, you don't get to see your face in a webinar, okay? To be able to talk to us, use the chat line. If you go down to the bottom of your page, with your mouse, you should a chat should open up, and you can chat to people. You can chat to all your participants, or you can chat to just the panelists. Okay. If you have any questions or answers, that's how you ask them at the meeting. And I think that's basically all I need to explain. Is there anything else I need to explain, Dave, Randy? Okay. We're just waiting for a few more members to show up and get on our way.
Yeah, it's only a couple of minutes past.
Yeah. All right, Randy, talk about the talk channel. RASCN talk, how to get onto it for me.
Okay.
Just 1 second, I gotta go.
We have a member chat facility. We're calling it RASCNL Talk. It's on the Google groups.io platform. If you'd like to join, some details on our website. I don't think I can, yes, I can share my screen. I can show you. Whoops, there's Gary. So here's if there's a web interface to the groups as well. If you go to the web interface, you'll see this. You can read all the messages. You can also check out some of the things we can do: polling, chats, calendaring, photos, for example. Everything that's posted as a message also gets put up as a photo in the gallery. You can check through some of the stuff that was been posted the past week or so, and everything from the moon to the sun, all over the moon, and these sorts of things. So that's the photo gallery. That's automatic. As a subscriber, you can change how you get the material, either as individual emails or digest in several formats, daily, again, several formats of the dailies, if you don't wish to receive each individual message. So get in contact with our center address if you'd like to be added to it. It's info@stjohnsrasc.ca, and that's all I'm going to say.
Okay, thanks, Randy. Just before we introduce the thing, we got a few more seconds. I'll give a chance for more people to come on. A lot of people have been asking, I don't know if you can see me or not, about how do I get focus? And you can buy these beautiful things here. They cost about anywhere from 10 to 20 bucks, depending where you get them. And this is a focuser. Now, if
Are
you don't
you-
have money, what?
Can you take over the session? There you go.
Yeah. Okay, then I can do a stop share. There we go. We're back to where we're at. Oh, well, that's funny that you don't have one. Anyway, there's these expensive ones, or you can use the covers to your food containers. You can buy them at Walmart themselves. Drill 2 holes. I drill 2 holes and a triangle rather than 3 holes. And the reason for that is that when you focus it, the 3 of them come together. And if you go past focus, you'll see one with the triangle, and you know you've gone past focus. So you go the opposite direction. And if you go the other direction, it tells you that you've gone past it. And when it's one cell thing, it's in focus. Just a little tip. Anyway, enough of that. I hope everybody's enjoyed. And then I'm going to go pass it over to Dave, who's going to introduce our speaker for tonight.
Yeah, before we get to that, I noticed there's a question in our question section, question and answer, from Mark Pippi about, he's wondering if he can see who else is listening and participating. So so for regular members, regular participants, you can only see those that are set up as panelists. So that's the 5 of us on the screen. Hopefully you see 5 of us. However, I think if you go to the chat and if you type in a message, there's a drop down where you can pick all panelists, or I think it'll show you who else is available, because you could actually write a text to them directly. Now, I don't know, Randy, if regular members can see everybody or just the panelists.
Sorry, I don't know. I've always been a panelist, so I haven't played.
That's the best answer I can get without I'm in the same boat. I'm in as a panelist, so I don't know for sure. But I think your best chance to see who else is there and possibly send them a message privately is in chat. Okay, Mark says he cannot see who else is attending. Okay, so and this is just the nature of the fact that this is a webinar and not a meeting, and the webinar is more locked down in terms of the amount of participation. Which makes it a bit more secure for us, because there have been some issues with Zoom in the past and hackers trying to hack in. But it does cut back on the amount of interaction, unfortunately. But we do have the question and answer, and we also have the chat window. Pretty sure, Mark, if you send the text to to everybody, that everybody gets to see that. There's you should have an opportunity or an option to pick panelists and all attendees for the chat. All right, so I'm just going to share a screen myself very quickly. How about now?
Yeah.
Okay. All right. So. All right, so our speaker tonight is Dr. Alison Leitch. She is an associate professor with the Department of Earth Sciences at MUN and has been with the university since 1998. Dr. Leitch obtained her PhD in geophysical fluid dynamics at the Australian National University. She has held postdoctoral fellow positions with mechanical engineering and earth planetary sciences departments at the University of Toronto, and has also held research fellow positions with the Research School of Earth Sciences and at Australian National University and Minnesota Supercomputer Institute, University of Minnesota. With background in physics, geophysics, and magma dynamics, Dr. Leitch's work spans from the laboratory to the field. Her most recent projects have involved investigations of traditional and non-traditional geological targets using a range of geophysical techniques. I think it's also fair to say that Dr. Leitch has a history with astronomy. She's had a lifelong interest in the subject. During high school, she was a founding member of the Canberra Astronomical Society in Australia. And for the past several years, she has happily volunteered within the Earth Sciences teaching staff to teach the Earth Science 2150 course, which is on the solar system. This course is put off every fall, and I had the pleasure of sitting in on the course last year, and it was actually quite enjoyable. The course is often scheduled as a weekly evening course, so may be of interest to other members in our group. Anyhow, without further ado, I'll turn it over to Dr. Leitch. Hopefully I've stopped sharing my screen.
Okay, have I got that on screen now?
Yep, looks good.
Oh, okay. So I was originally, the subject of this talk is substance use in the solar system for chemical substance use. And originally I was thinking of doing the whole solar system, and I picked together about 200 slides and realized that it was more of a course than a talk. So it's really, this talk is really about substance use in the planets. So here is just a rogues gallery of the planets, which are sorted according to their distance from the sun, and their sizes are correct, but of course the distances between each other are not. And as far as the substance use of these planets, how they use chemicals in their makeup, you can divide it up into three groups. You've got the terrestrial planets, Mercury, Venus, Earth, and Mars. You've got the gas giants, Jupiter and Saturn. And you've got the ice giants, Neptune and Uranus. And if you want to include Pluto as a planet, that makes a fourth group. So the substances in the solar system vary their roles from one end to the other. Take, for example, the substance nitrogen. Here's a nice picture of the Earth's atmosphere taken from space on the left. And on the right, we have a picture of Pluto taken by the New Horizons spacecraft and backlit by the sun. And it also has a nitrogen atmosphere. But on Pluto, nitrogen also exists as a solid. And here's a picture of glaciers of nitrogen flowing out onto a plain on Sputnik Planum, which is a great big area on Pluto. And in the past, perhaps when Pluto had a thicker atmosphere and was a bit warmer, we might have actually had nitrogen in a liquid form flowing in rivers and lakes on Pluto. So the outline to my talk is this. I'll just talk about the common elements and compounds that I'm talking about, and then spend a bit of time talking about the Earth, my favorite planet, and to sort of as an illustration of all the things, all the roles that the common elements and compounds play. Then talk about the terrestrial planets, and then in the second part of the talk, divided up between the gas giants, the ice giants, and Pluto. So here are 9 key elements in the solar system that I'll be talking about. So this is the wonderfully organized periodic table, at least the first 118 elements of it. And the 9 key elements for the solar system that control the most of the composition and dynamics are these 9 here: hydrogen and helium, carbon, nitrogen, oxygen, magnesium, silicon, sulfur, and iron. Now, these aren't the only important elements, but I'll get by with just describing them. There are all a bunch of other ones that are very important, but don't have time to get into them. So why did I check these 9 elements? Well, because they're common, that's one thing. So here is a list of the 10 most abundant elements in the universe. And you can see that my 9 elements are in this list. So the one element that I'm not going to talk about is neon. Neon is another inert gas like helium. It doesn't really have much of a role, and it's much less abundant than helium, so I won't talk about it. So a couple of things I want you to notice. First of all, hydrogen and helium, as you are no doubt well aware, are the main components of stars, and so you expect them to be quite abundant in the universe and the solar system. The third most common element in the solar system and the universe is oxygen. And notice that oxygen there is actually, as far as an atom by atom goes, it is more common than all of the elements underneath it combined. So you would expect then that oxygen if it's going to try and react with all the other elements in the universe. So these 9 elements are important building blocks, which I'll go over. First, from the point of view of elements, hydrogen and helium are present in the sun, the gas giants, and the early atmospheres of the other planets. Nitrogen is in the atmospheres of the planets and the moons, and the icy crusts in the outer solar system. Oxygen is present in the atmosphere of the Earth, and not very much else as a gas, because it's mostly reacted with other things. Sulfur is important as an antifreeze, particularly in the cores of planets, but also in the magmas of Io, Jupiter's moons, which of course I'm not going to talk about today. And iron is in the cores of the planets and some moons. So those are the elements or molecules where they're combined with themselves. In addition, you combine some of the most common elements together and you get some more common and very important molecules. So first of all, there's water, H2O, that's in the oceans and atmospheres and crusts. Methane, which you may think of as a product of swamps and cattle and fracking. This is an important atmosphere in the gas giants and lakes on Titan and ice in the outer solar system. Carbon dioxide is the major element of the atmospheres in the inner solar system, except for the Earth. And ammonia, NH3, you might think of that as a cleaning material, but it is very important in the atmospheres of the gas giants, and it also acts as an antifreeze in water. And you combine all the others, magnesium and silica oxidized, those make up the rocky mantles and crusts. So all rocks, I'm going to consider from the point of view of this talk, are made up of magnesium silicates. Oh, and one other thing I might get to mention, tholins. So if you just look at this little diagram, it's just a complex molecule made up of some of these common elements, and the R's could contain oxygen. All right, so to explain why there is a variation in the roles and the concentrations of these elements in the different groups of planets that I've mentioned, we appeal to the condensation theory, which is basically says that in the early solar system, and now too, it would have had a very strong temperature gradient, and the solar wind would have blown out those elements which were gases at high temperature, and then just blown them out into the outer solar system where they might have been able to condense. So these are volatiles, they're called volatiles, hydrogen, helium, methane, and water in particular. These compounds and elements, they would be blown out, and that's why they're more common in the outer part of the solar system. So starting off with the Earth, the most interesting and dynamic planet that we know of. Here is a picture of the Earth from space on the left, and then a topo map on the right, which is just an elevation profile. And I'll be showing a few of these. So just in general, blue means low elevation, and the higher elevations are sort of reds and browns and that sort of color. And on the Earth, if you look at this, you can see that the Earth has a very distinct 2 levels of the crust. You've got the ocean floors and you've got the continents. So, looking at the inner composition of the Earth, we can divide it up into, first of all, is the inner core. Now, the inner core is a white-hot ball of solid iron, about the size of the moon, and it is hot as the surface of the sun. So it would glow white if it was laid bare. The outer core is a sea of molten iron with sulfur within it, which is about 3,000 kilometers deep. So the outer core would then be about the size of Mars. And then we have the mantle, which is made of rock. It's hot too. It's about 1,300 degrees. And though it's almost completely solid, it is hot enough that it's ductile. So it does flow at a rate of a few centimeters a year, compared to the outer core, where it's a few centimeters per second that you get motion in there. And then we have the crust, which is also magnesium silicates, but it's a bit more silica. The crust has generally been sweated out of the mantle by melting it a little bit. Moving on, we have the atmosphere. That's mainly nitrogen, oxygen, water, and CO2. So nitrogen and oxygen are the main ones, but the others, hydrogen, water, and CO2, keep us nice and warm. The liquids, oceans, is mostly in the oceans. That's liquid water. And then we have the ice caps, which are solid ice. So the oceans can be 4 kilometers deep, and the ice caps can be up to 4 kilometers deep, as solid ice as well. And the atmosphere is a very thin atmosphere, and most of the action is within 10 kilometers of the surface. Now, the most important role, you might say, of the core of the Earth is that we have the magnetic field of the Earth, which is generated by electric currents in the outer core. So the outer core is it's a turning over because as the solid iron core is forming, sulfur, this light element sulfur, is sort of released, and it sort of stirs it up. And that is essential for a magnetic field. So you want to have a geodynamo. You need, first of all, an electrical conducting region that's fluid enough to convect. In this case, on the Earth, it's molten iron, and then some mechanism to stir it. So there's about 3 different ways of stirring it, but heat loss, release of sulfur, and some people think that the actual turning of the planet is important. So the magnetic field is hugely important because it deflects most of the solar wind. So it protects us. And without the solar wind, without the magnetic field, the solar wind would strip away the atmosphere of the Earth and would also bombard the surface with killing radiation. So moving up, that's what motion in the outer core is important for. So what about the mantle? So the mantle of the Earth, which, as I said, it's sort of ductile and it's turning, and it's responsible for plate tectonics. So this is something which is unique to the Earth. The surface of the Earth is divided up into these sort of rigid plates, which interact at their boundaries. So at their boundaries, you would see all of the volcanism and the earthquakes and so on occur at the plate boundaries. So if you look at Newfoundland, which isn't very clearly shown in this map, you'll see that it's so safely far away from the boundaries. And that's why we don't get any earthquakes and volcanoes here. This is just a cross-section showing you the sorts of things that happen at these plate boundaries. So at where the plates are pulling apart, that's in the middle of the oceans, the hot mantle comes close to the surface of the Earth. It partly melts, and you get a whole ridge of volcanoes in the middle of the ocean. And then, on the other hand, when one of the ocean part of the crust hits a continent, and then it goes down into the mantle, and then you get another type of volcanism occurring. And I'll just put this picture up to show you that the result of plate tectonics is elongated ridges and mountain ranges where the plates are pulling apart and coming together. And I mention this in particular because even though other planets might have this sort of 2 levels of elevation on their surface, none of them has these lines of volcanoes like we do on the Earth. So we've looked for plate tectonics on other planets. It seems to be unique to the Earth. The composition of the Earth's atmosphere, remember, it is also unique. So the Earth is a very unusual planet in many ways. So it's unique in the solar system by having abundant oxygen and very little carbon dioxide. So carbon dioxide is rising. It used to be 0.03%, now it's 0.04%, but still it's a trace element in the atmosphere. And why is oxygen so unusual? Well, I mentioned that it is the most chemically reactive of all of the common elements. So it reacts with all the other elements. And for example, it reacts with iron to produce rust and carbon to produce carbon dioxide. And so, given the chance, it just sort of oxidizes all the rocks and everything around it. And so you don't expect to see it just floating around free. And of course, we know that the reason we have oxygen in the atmosphere is because of photosynthesis. So this is an amazing evolutionary step where life on Earth was able to use the light from the sun to grow. So they use the energy of the sunlight to break carbon dioxide, importantly, into carbon and oxygen. So the carbon they use, for creating their cellular structure, and then the oxygen is released into the atmosphere. That's one of the reasons why we don't have a lot of carbon dioxide in our atmosphere. But it's not the main reason, at least directly, because if you look at this is a graph showing you, well, where the hell is the carbon dioxide that should be in our atmosphere? And you find out that, well, some of it is dissolved in the oceans, a little bit in the biosphere, and most of it is in rocks, limestone rocks and fossil fuels. Now turning to the importance of water. So water, again, there's only about 1% of it in the atmosphere. Again, it's a very important element on the Earth's surface, and it's responsible for weathering down the rain and glaciers and so on. Most of the glaciers, they create sedimentary rocks, and they create rivers and gullies. So in summary then, the 8 key elements on the Earth, how are they divided up? We've got the iron and the sulfur in the core, the magnesium, silicon and oxygen in the mantle and the crust as rocks. We've got nitrogen and oxygen in the atmosphere, water in the oceans, ice caps in the atmosphere, and CO2 in the atmosphere, biosphere, oceans, and the crust. And they're important, their roles in the dynamics in particular is the outer core creates the magnetic field. Dynamics of the mantle creates plate tectonics and volcanism. And the atmospheric dynamics, which is driven by water, creates weathering and different sorts of rocks on the surface. Moving on to the terrestrial planets, here they are in order from the sun. And we've got Mercury on one side, Venus, the Earth, which is the biggest of the terrestrial planets, only a little bit bigger than Venus, and Mars. And we can include the moon's, Earth's moon, because if it was in its own orbit, it was orbiting the sun instead of the Earth, it would be a perfectly respectable terrestrial planet. Looking at the composition of the terrestrial planets, they're all very similar. And that's why you can all group them all together. They all have a metallic core, which contains iron and sulfur. They all have rocky mantles, silicates, and a rocky crust with a slightly different sort of silicates. But only the Earth and Mercury have magnetic fields. So Mercury has a huge core. It has takes up most of the radius of the planet, 83% of its radius, compare that with 55% of the Earth's core. And originally people thought that Mercury would be completely solid because it's a small planet, it would have time to cool down. And it turns out that's not to be the case, and the reason is because it had lots of sulfur in it. Remember, sulfur is an antifreeze. And so not only do we have a solid inner core and an outer core which has got a lot of a molten core, which is iron and lots of sulfur, it has an anticrust, what they call an anticrust, which is actually another solid component, which is iron sulfide. And then the mantle of the crust is similar to the other planets. So Mercury has a magnetic field, which is about 1% as strong as the Earth. So here we have Venus and Mars. So why don't they have magnetic fields? So remember, there are two things that you need. You need a molten conductor. Yes, we've got molten conductor. We've got molten iron in the center. And it has to be in motion. And Venus doesn't have a magnetic field. It's probably because the core is completely molten. So there's no solid inner core to release the sulfur and drive convection. And also it has a slow rotation. And Mars, it definitely has a partly molten core. It has a similar rotation to the Earth, and there are 3 different theories on why it doesn't have a magnetic field, and so they're sending some spacecraft up there to try and figure out which one of those it is. The Earth's moon also has a similar sorts of structure as the other planets. It's got an inner core, solid iron, an outer core, molten iron and sulfur, a mantle and a crust of silicate rocks, and then it has its something that's a little bit unusual compared to the other planet. It has a partial melt region just outside the core. This is a sort of partial melt region that we see on the Earth, very close to the surface, and it was responsible for volcanism. So all the partial melt thing that could cause future volcanism on the Earth's moon is way down in the center of the planet. So it's not volcanic at the moment. So the moon had a magnetic field in the past. We know that because of the rocks brought back by some of the Apollo astronauts, but it doesn't have that in the minute at present time. So what are the consequences of the magnetic fields? It's not just the magnetic fields, the gravitational fields and the distance from the sun go into it. But for Mercury and the moon, no magnetic fields or a weak magnetic field means that there's no atmosphere. It's just been ripped off, if it ever had one, by the solar wind. On Venus, which has a very thick atmosphere, it seems, but no magnetic field, it seems that that's one way that the water has been removed from the surface, from the atmosphere of Venus. Venus is very dry. And then for Mars, it has a very thin atmosphere. And again, that's because a lot of the atmosphere has been stripped away by the solar wind. And on the Earth, it's just perfect. Looking at the tectonics, that's motion in the mantle and the crust. The moon and Mercury seem, at the present time anyway, to be more or less dead as far as motion. They don't have any plate tectonics. Their mantles are not moving, it seems. They're just sitting there. But if you look at the surface, like particularly on the moon, you can see those dark marias. That's where there was some huge outpourings of lava in the past. So early in its history, there was a lot of volcanism on the moon, and the same with Mercury. If you look at Venus, it doesn't have any plates, but it's covered with volcanoes. They seem to be mostly dormant. We haven't been able to actually catch one in the act of erupting. But notice there's the high points in this elevation maps. They're not arranged in lines. They're just sort of scattered all over the surface. So the model for Venus is that, yes, its mantle is convecting. So Venus, the rocks are actually moving like they do on the Earth, but it's all underneath the crust. And so the plates are not sinking back down into the mantle. And one of the reasons that people think this might be is because of that there's some little water, that water might have the added advantage in helping to sort of lubricate plate tectonics on the Earth. Looking at Mars, it doesn't have very many volcanoes, but it does have some enormous ones. Olympus Mons is the biggest volcano in the solar system, and it's sitting on or near to a bunch of other volcanoes, dormant volcanoes probably, but they might have been erupted fairly recently on this big, enormous plateau. And the thought is that, again, in the past, perhaps there was some overturning, sort of simple overturnings, like one cell amount of convection in the past, unlike Venus, where you think it's, more irregular. Looking at the surfaces and the atmospheres of the terrestrial planets, the surfaces of the Moon and Mercury look very similar. They're very old and heavily cratered. And so this at the bottom is actually a picture of the surface of Mercury. Looks pretty similar to the Moon. And on the right here, we have two pictures taken by the astronauts on the surface of the Moon. So we can't really tell about the surface, what the surface looks like on Mercury, but on the Moon, it's covered with this fine grey dust called a regolith, and it's several meters thick. And it was a bit of a concern when the astronauts went there whether they were going to sink down into dust, but it turns out it's sort of like fresh snow, and the footprints just sort of sink down a few centimeters. Neither of these bodies has any atmosphere to speak of, but they do have ice caps, sort of. So both Mercury and the Moon have no seasons. So their poles are sort of pointing straight up and down relative to their orbits. And so they never tilt towards the sun. And there are regions on Mercury's North Pole. You see, this is a topo map again. You can see this blue area. There's sort of a low at the North Pole of Mercury. And in the craters there, they would never see, the sun would never get into these craters, and they've detected ice in these craters, water ice. And the same in the Moon's south pole, they have detected water ice on the south pole of the Moon. What does the surface of Venus look like? Well, we only have a few photos. They were taken by the Soviet landers in the 1970s. And these strips here were sort of color strips, so they know when they took the photographs, they could get the colors right. So it's, it's a sort of a baked silicate crust. Venus is very inhospitable. And the reason is that all of the CO2 that is trapped in the rocks on Earth, if you took all of that carbon dioxide that was trapped in the rocks and the oceans and you put it into the air, you would have Venus. Venus' atmosphere is 90 times as thick as the Earth. It is mostly carbon dioxide, 96.5% carbon dioxide. It's only about 3%. Most of the rest is nitrogen. But the amount of nitrogen in Venus's atmosphere is similar to the amount of nitrogen in the Earth's atmosphere. The big difference is all that CO2. And if you look at the rest of the trace elements, you've got all of the usual suspects. Compare that with the Earth. It is a completely different atmosphere, even though they're supposed to be sister planets. So what's it like then with that thick atmosphere? It is, if you went to spend a day on Venus, you wouldn't survive very long because you'd be crushed. The atmospheric pressure is about the same as about a kilometer down in the oceans on Earth, and that's enough to even crush a submarine. So it's a long, stifling, dry, crushing day on Venus. The daylight lasts 8 Earth weeks. Venus has got a very slow rotation. There's a lot of lightning, but the rain doesn't reach the ground. You get rain in the clouds, but it evaporates before it reaches the ground. And that rain is not water, it's sulfuric acid. And it's hot, very hot. So it's about the same temperature on Venus as it is on Mercury, even though Mercury is much closer to the sun. So it's 740 degrees Celsius. That's enough to melt zinc all over the planet. So no big surprise that there haven't been too many spacecraft that have landed on the surface of Venus. And there are light winds, sort of like the bottom of the ocean on the Earth. Mars, looking at its surface, it's the red planet because all the crustal rocks are oxidized, rusted. So, you know, I was sort of not. I was exaggerating when I said all the iron was in the core. There's plenty of iron also in rocks, and the rocks on Mars's surface. That's where all the oxygen is, and there isn't any oxygen in the atmosphere. This is what the surface looks like, one of the surfaces. It's sort of like a red desert on the Earth. We've got plenty of pictures of Mars's surface taken by the NASA rovers. And there's plenty of evidence of liquid water in the past. First of all, again, here's our topo map of Mars, and it features this huge canyon which was cut through by water, Valles Marineris. This is in fact the biggest canyon in the solar system, and it is from one end to the other. It would be about the size of North America, the width of North America. So it's much bigger than the Grand Canyon. We also have sedimentary rocks on Mars. So remembering that sedimentary rocks on the Earth are laid down by water, that's probably how these rocks were laid down as well. We also have evidence just of these dry river valleys. They look exactly like rivers, of course, a few craters as well, but river valleys. And then here is a valley which comes down and dumps water into what would have been a lake or an ocean in sort of these terraces, deltas, terraces. And then if you look at some of the craters, they have this sort of splatter pattern, which again, you don't sort of see when you have dry material. So this would be probably hitting something with permafrost in it. So in the past, Mars probably had oceans over half of its surface. Now, however, it has ice caps. That's where we have water ice in the ice caps of Mars and in permafrost. So here on the bottom left, we have a picture of, here are some sedimentary rocks. And here are these gullies coming down as some liquid, probably permafrost water, is being released. And this is one of the ice caps. Now, as well as having water ice on Mars, Mars's ice caps are also made of carbon dioxide dry ice. So looking at the comparative atmospheres of these planets, you can see that, so here's Earth in the middle, and we've got the altitude here on the left, and they're scaled so they're the same altitude. And these red lines are the temperature and pressure on the other side. So if we look at them, so here's the Earth, and we've got so most of the atmosphere is close to the surface, and we've got water clouds, which are water ice, and water droplets in the bottom part of the atmosphere. On Venus and Mars, they have similar amounts of carbon dioxide and nitrogen, but otherwise they're completely different. Venus has got like 100 times as much atmosphere, and Mars has less than 1% of the Earth's atmosphere. Venus has sulfuric acid clouds and sulfuric acid rain, and Mars has carbon dioxide ice and water ice clouds and no rain and lots of dust. The gas giants, Jupiter and Saturn, and you know that they're called giants because That's how big they are compared to the Earth. These are completely different than the terrestrial planets. Like the Sun, they're mostly composed of hydrogen and helium. And unlike the terrestrial planets, in the terrestrial planets, there's these sharp differences. You've got the atmosphere, you've got a solid surface, you've got sharp interface between the core and the mantle. Here, everything is fuzzy. And the composition changes very gradually. So here we start off with hydrogen as a molecular state, what we're used to, and it gradually turns into a liquid, and then it turns into a metal. So it behaves like a metal. It's conducting electricity, and then the fuzzy region between the two forms of hydrogen, we have helium rain. Although there are no clouds associated with it, just droplets of rain falling down into the interior. And even the core, where everything else is fuzzy. It seems to be partly dissolved in the bottom part of the hydrogen and helium substances. So we have a convecting metallic hydrogen, and so these gas giants have massive magnetic fields. So here is Saturn, and the rings and the inner planets are all inside the magnetic field. Jupiter's magnetic field is even bigger, is 18,000 times stronger than the Earth. So, on the Earth, the magnetic field is a really good thing. It protects us. It makes the Earth livable among all the other lockout features of the Earth. But for Jupiter, is it a good thing that it has a big, huge magnetic field? From our point of view, from the point of view of exploration, there's good things and bad things. The good thing is that, again, a lot of the inner Galilean moons are inside the magnetic field, and the interaction is pretty interesting. But on the other hand, it also makes it very dangerous for spacecraft. The spacecraft are a bit nervous about being damaged by this huge magnetic field. If we ever even thought about trying to colonize Jupiter, the magnetic field itself would make it impossible. It'd be very, very unhealthy for human beings. One nice thing is you get nice auroras because of the magnetic field interaction with the solar wind. The atmospheres of the planets are very colorful and dynamic. This is a sort of a picture of Jupiter, as you would know, and these flashing dots are the shadows of the moons. So Jupiter's got very strong winds. They're hundreds of kilometers per hour in opposite directions. And these circular features are storms, long-lived but not eternal. The most famous one is the Great Red Spot, which was first seen by Cassini more than 300 years ago. And here is the Earth in comparison. So it's been around for a long time. And there are other little spots in the atmosphere as well. You see these ones. And then when Juno arrived, more of these were revealed. So this is the south pole of Jupiter. And you can see it is just surrounded by these long-lived hurricanes. It looks completely different than the equatorial pattern that we see mostly from Jupiter. This is Saturn. It's blander and natural colors. But you can by looking at the infrared spectrum, it looks a little bit brighter. And the differences in colors, again, are due to ammonia ice clouds. And Saturn is even windier than Jupiter. It's 1,500 kilometers an hour around the equator. Here's a picture of the atmospheres of Jupiter and Saturn. And so, on the Earth, the clouds on the Earth and on Venus are not made of the major components of the atmosphere. So the major components of the atmosphere on Venus and Mars is carbon dioxide, which is transparent, and the clouds are sulfuric acid. And on the Earth, they're water ice and water droplet clouds. So similar on Jupiter and Saturn, where the major elements of the atmosphere are hydrogen and helium, that the clouds are formed by these ices: ammonia ice, ammonium hydroxide ice, which is this substance here, and water ice. And Saturn's rings are mostly water ice. They've got some dust there as well. And they actually have their own very, very thin atmosphere of hydrogen and oxygen. The ice giants are Uranus and Neptune. And they're giant compared to the Earth, but not nearly as big as the gas giants. And their compositions, again, different. You have an upper atmospheric clouds. In this case, you have methane ice clouds instead of ammonia ice clouds. The atmosphere is hydrogen and helium, like the gas giants, but you've got more methane here. And then further down, the mantle is not made of molecular hydrogen. Instead, it's made of water, ammonia, and methane. And the core, well, I suppose it's probably rock iron and iron. People have speculated that there might be a layer of like solid carbon, which is diamond, just around the outside of the core. People like to speculate, but the fact is, very little is known about these ice giants. There's only been one spacecraft going back past them, and that was in the 1980s, Voyager 2. So they take everything people say about these planets with a grain of salt. You might want to wonder, why are they called ice giants? Because like all these big planets, they're usually hot. And the reason is, it's not that they've got ice inside, or maybe there's some solid ice and solid water in the core, but it's because these compounds that make it up, hot water, ammonia, and methane, are what astronomers call volatile ices. And that's why they're called ice giants. Again, they have magnetic fields. And remember, you need a fluid electrical conductor. In this case, it turns out that the mantles are electrical conductors, sort of like salt water. And you get some weird magnetic fields produced here. Now, remember that we've only had Voyager 2 going past in one, very brief sweep past both of these planets. And so they've only caught a very, very small part of the magnetic field. So again, they don't really know what the magnetic fields look like. So finally, finishing off with the dwarf planet Pluto and its biggest moon, Charon. And there is the moon for scale. So the Earth's moon is bigger than Pluto, and the Earth is about 4 times the diameter of the moon. So they're pretty small. Now these the red colors that you see on the surface of Pluto and on one of the pole caps of Charon are due to these tholins that I mentioned at the beginning. Here again is a somewhat speculative model of the interiors of Pluton and Charon. So this is again a completely different structure to the other planets. We've got we thought they have a rocky core and like a solid blanket of water ice on the outside. And then in the Pluto's case, there's a speculation that we have a liquid underground water, layer. This is something that has been seen in some of the moons of similar sized Pluto, in the inner solar system. But in order for it to be still liquid, at the distance that Pluto is from the sun, you would have to have quite a bit of ammonia antifreeze in it. And then, so it's water ice on top of rock. And then on the surface of Pluto, we have ices of nitrogen, methane, and carbon monoxide. And on Charon, we also have ammonia ice. So these ices, which we saw as just occurring in clouds or churning around the insides of the gaseous planets, and now in the outer solar system are respectable solid ices on the surface. So they were able to find 4 different sorts of ices. So the main one is water ice. That's the main component of the outer part of Pluto. But then there are these other ices. So these are sort of veneers over the surface of the mainly ice. So we've got nitrogen, methane, and carbon monoxide ices. So water ice on Pluto is as strong as rock is on the Earth. So the mountains are made of ice, water ice. Nitrogen ice is much weaker and flows downhill. So there could be water ice volcanoes on Pluto. Again, you know, we've just had one spacecraft rushing past, so we don't know. But this feature here in the middle is about 4 kilometers high, and it's got a summit depression, and so it could be an ice volcano, and it doesn't have too many craters on it, so it's probably young. So this is one of the reasons people think there might be an underground ocean on Pluto. The nitrogen ice, so the plains of Pluto are covered with nitrogen ice, so it flows over periods of months and years, and so it can't really support any topography. You don't see any mountains made of nitrogen ice. And here, this feature here is called Sputnik Planum, and it's covering what was probably a crater. So there was a massive impact at some point, and it's been filled up because it's a depression. It's been filled up with this thick layer of nitrogen ice with some of the other ices in there. So there are nitrogen ice glaciers. So the nitrogen, so this is the edge of Sputnik Planum, and these high hills, of course, they're made of water ice. And then in between the gullies of the mountains, you have glaciers of nitrogen ice coming down, and these red lines where they think the edges of the outflow are from these glaciers. Now, nitrogen ice is heavier than water ice, even though it's weaker. So you get these water ice icebergs actually floating on the nitrogen ice in the Sputnik Planum. Just to show that there are other sorts of ices here. These are some high ices, not so common, methane ridges found in the mountains. And finally, the atmosphere, it contains, as well as nitrogen, these smog layers of hydrocarbons. So the idea is that the cosmic rays come in and they convert the methane into other sort of longer hydrocarbons, the sort of sooty dark things, and they fall down onto the surface. So these haze layers then are sort of methane smogs. Okay, in summary then, these are the 9 most common elements in the solar system, and you can just about explain everything, the structure and dynamics of the different planets in the solar system based on them. So these are 9 of the 10 most common elements of the universe, and they change their roles from the inner to the outer solar system. The planets in the different groups change their composition from surface to core in different ways. So for the terrestrial planets, they have a CO2 atmosphere a rocky crust and mantle, and a molten iron core. So here where all of the magnesium and silicon are in here. These are the volatiles, predominantly CO2, or it would be if we didn't have oceans and the biosphere on the Earth. And molten iron, the heaviest, sinks to the bottom. The gas giants, on the other hand, they're mainly made of helium and hydrogen with sort of a rocky core. And they've got the most common clouds they have are ammonia clouds. The ice giants, they have methane clouds in the hydrogen helium atmosphere. And they have an interior, which is a liquid, hot liquid made of water, ammonia, and methane, and a rocky core. And Pluto has a nitrogen atmosphere, hydrogen, water crust, maybe a water subsurface ocean, and a rocky core. And the magnetic fields, they're common but not ubiquitous in the solar system. And in the terrestrial planets, they're caused by stirred molten iron and sulfur. It needs to be stirred. They all have sulfur, but they're not all stirred. The gas giants, it's stirred metallic hydrogen. And on the ice giants, it's a stirred solution, water solution of ammonia and methane. And Pluto doesn't have a magnetic field. And volcanism on the different planets is due to, on the terrestrial planets, it's molten rock, and on Pluto, it's water. So I'll leave it there. Thank you.
Thank you, Dr. Leitch. We have some questions. I think Dave and Doug were doing questions, but I don't see Doug on the panel, although he says I have him here as being on the panel.
Oh, there he is.
Okay. Oh. Oh, I thought I'd lost you again. Okay, Dave, Doug, you want to do the questions?
One question from Mark. How can you tell what the core of a planet is?
Well, partly it's a bit of a circular argument. As you look at what is the common elements in the universe, and then you measure their properties, like how dense they are at certain pressures, and when they would be liquid and when they would be solid. And so that's, and also I suppose as far as terrestrial planets go, if they look at the compositions of meteorites, which are sort of leftover bits from the solar system, they find iron and rocks. And so the only common element that's dense enough and heavy enough to make up the cores of the planet has got to be iron. And sulfur, again, that is again a bit more speculative. Nobody really knows what the elements are in the cores apart from sulfur. I mean, apart from iron, but sulfur is a reasonable guess. And as for the others, again, it's a matter of, well, what are they made of? How heavy are they? How dense they are? And as far as the ice giants go, yeah, that's pretty iffy. I don't know. I'm not convinced they really understand what the interiors of the ice giants are.
There's a question here from Jim. He's asking, why has the atmosphere of Venus not been stripped away by the solar winds?
Well, it's a competition between the gravitational field of the planet and the solar wind. So Venus probably had a even thicker atmosphere to begin with, and it is sort of being stripped away partly, but it's yeah. So it's just because it's a big enough planet to hold on to it.
Well, we have a question from Mike. On which planet is neon most abundant?
Neon?
Yes.
Neon? I don't know, but it would be I don't know actually. So I think it would probably be the gas giants or the ice giants.
So I have a question myself, based on a lot of what you talked about in terms of the planet compositions and atmospheres and lack thereof. And I know you didn't get into some of the moons, which in
No
their own
time.
right are interesting. Yeah, especially the moons of Saturn and Jupiter. But where would you say is the most hospitable, or at least inhospitable, place for us humans to try and set up on outside of Earth?
That's a good question. Probably Callisto, which is the outermost of the Galilean moons of Jupiter, because it's the outermost one. You don't want to live on Io because it's too volcanic. And the other moons inside are maybe a bit too close, and the magnetic field is a bit too strong. So, but I think we would be better off maybe setting up in the asteroid belt series, perhaps.
I'd like to ask one. Which planet do you think we should explore next? Or which moon? Seeing that we seem to have found 3 moons that may have life, which one would you like to see a satellite or a rover visit?
Let's see. I'm trying to remember. Oh, the icy moon of Jupiter. It's not. What is it? The name escapes me.
Europa.
Europa. Yes, that's where I'd like to go first. From a point of view of looking for life, from the point of view of an interesting moon, I would really like to go to Titan, the largest moon of Saturn. It has an atmosphere that's it's very cold, of course, but it's got a very active Earth-like almost.
Has lakes and methane mountains, isn't it?
It's got methane lakes and methane rain and a thick atmosphere and ice volcanoes. It's got it all. But again, very cold.
Yeah, I'll just throw out there, we have many comments in the chat about the great talk, and thanks for the talk, great presentation. Thanks for the great talk. Thank you again, Dr. Leitch, for joining us for this presentation.
Okay, you're very welcome. Thanks.
Yeah, you don't get too many claps over these things. But there's lots of, he only touched the tip of the iceberg, I would say, on the comments in the comment area. So your talk went over really well. We have something to give you. Of course, we'll have to send it to you because of this time. You're more than willing to stay and listen to the rest of the meeting, or you can bow out, whichever you'd like to do. Okay.
Okay. Well, thanks.
Okay.
I might leave. I've got to feed the cats.
Anyway, I'm going to get Randy to talk for a second here. Randy's got something to say, and he was going to also talk on, I guess he's going to ask you what you want, but he was going to talk on annual reports and annual general meeting. But you had something to say, Randy?
Yep. I think all members should by now have gotten a notice of the annual general meeting coming up on June the 7th. It's at 7:30 our time. This is in lieu of a General Assembly. and you will need to register for the Zoom session. So try and find your email from that. Along with that is the annual general report, including our own submission. So feel free to peruse that. It should be available on the national site. Log in and go down through, so I think it's in the governance section. So that's all I have to say there. Was there something else, Gary?
Okay, you did both the annual report and the general meeting.
Yes.
How about summer activities and virtual? There's also a poll up right now. You can vote on these two questions. We're trying to get some answers. So please free to put on the poll. So what you can talk, summer activities. Well, because the COVID, I was going to say, yeah. 19, we can't have meeting groups gatherings of more than 10. So someone has said virtual activities. What do you mean by that, Randy?
I was wondering, again, it doesn't look like we're going to be able to have any in-face sessions. Even in the dark, they won't allow us. Wondering what people interest would be for the summer. Would you, a number of us have been having hangout sessions on Google, and there's lots of other casual stuff on the go, and I don't know if people are interested in that. A lot of those things are at the last minute. You know, if you can't have a virtual observing session if it's cloudy unless you're going to study in clouds. So a lot of it does take place haphazardly. So I'm just wondering if people might express some interest in what they'd like to see us do. A number of people are, I think, geared up to do virtual observing, you know, showing what's looking in their telescope, etc. So maybe you could send your comments along.
And where would we send them to?
I can send them to the general information link, I guess, info@stjohnsresc.ca. Or if you're on the talk list, you can certainly express your opinion on the talk list.
Okay. Thank you, Randy. Next up on the, our next speaker for June will be Bernard Day, and he'll be talking about the dome on the hill. Bernard's one of our new members who has built a dome, an observatory from scratch out Twillingate Way, actually closer to Lewisport. He's a good friend of Jim. He built the dome himself right from scratch, and he's going to give a talk on how he built it and some of his pictures. Hopefully that will be the June meeting. And next we go to Nikolai. Are you ready, Nikolai?
Yes, I am.
Okay.
Can you hear me okay?
Yep.
All right. Let me try and share my screen. Okay, share screen. All right. Can you see that? Yeah.
Yes. Yep.
Okay.
It's also on the website.
What's that?
It's also mounted on the website.
Yes, yes, it is. All right, so I'm going to be talking about what you can see in the sky from St. John's roughly over the next month with naked eye, binoculars, or telescope. So this is it, starting with the solar system roundup in terms of sunrise and sunset and all the associated twilights. These are the times for that to plan your observing sessions. Currently, sunrise is at 5:16 and sunset is at 8:38. So a pretty long day as we march towards that summer solstice next month. In terms of bodies in the solar system, planets, here are the rise and the set time for each. Cross meridian time, which is when they are at their highest. Moving on to the sun, no surprise there. The sun is blank, as it has been for a while. We do have a telescope that you can borrow if you want to observe the sun. Never look at the sun without proper filters. In terms of planets, Mars is currently the most prominent morning planet. It rises between 1 and 2 hours after midnight as we go into June, and its apparent diameter will grow from 9 to 11.4 through June, meaning that observations of detail are finally becoming possible with medium-sized telescopes. And you can see a picture of that, which I am not revealing on purpose so that there's a bit of a surprise. It's not my picture, it's a picture of an amateur astronomer taken just about last week from Australia. As you can see, a good bit of detail there. So as Mars grows slowly into the summer and as it works towards its opposition date, which I want to say it's in October, it will become more and more visible, and you'll be able to see more and more. Uranus and Neptune will be rising several hours after midnight and will be observable later in the morning hours. If you rise early, you can check them out. In terms of evening planets, we do have 3 planets very prominent. Jupiter rising just before midnight and earlier as we go into June. So it will be very well placed for observing after midnight, and its globe will grow from 44 to 47 through June. So that this is the biggest planet that you can see through a telescope. Saturn is actually very close to Jupiter, and it will be through the summer. They actually have one of their closest conjunctions in a long time coming up. Saturn, it will be rising within 15 minutes of Jupiter, and so also visible after midnight for observing. Rings span 40 arc seconds wide and sport a 20-degree tilt from edge on. Venus is currently a prominent evening star, but it is sinking as it races towards its inferior conjunction on June 3rd, and that's the date when it will pass a mere half solar disk north of the sun, just narrowly missing a transit there. As you know, when Venus undergoes an inferior conjunction in June, it has a higher probability of that being a transit of Venus. But unfortunately, as you also know, that is just not happening for another 100 years. But it's just a cool fact to mention that it's a near miss. As it approaches that date, it will continue to become an extremely thin crescent because it's turning its night side towards us. And this is a picture of that progress taken by an amateur astronomer here. The credits are below from Romania. This is just a mere week apart. You can see that the crescent becomes thinner, and it also kind of envelops the planet more. So that will continue to become more and more pronounced over the next few days. So pretty cool to observe if you can. So that's the planets, comets. We do have a few comets on the go. That first one is visible, but it's pretty low right now. It will get better, I believe, in terms of altitude at least, not so much in terms of magnitude. These two are, I don't think they're visible here yet because of the constellation they're in, but they should become visible in the summer, probably in July. And they all have decent forecasts for their peak magnitude, definitely a naked eye object, so keep an eye on those. That fourth one, the Pan-STARRS one, it's definitely visible. It's not as bright as the others. Pretty sure we have pictures of it from our center. I want to say Mike Morrow has had a picture of it on the talk list. It's, you know, well positioned, just not as bright as the other ones. And that one is also not visible because it's in Monoceros, but I think later in the summer it will become visible. A couple of asteroids here if you are interested in that, and supernovae. If you have been following those, you will know that there's a few on the go. We do have some of our members having taken pictures of them. If you haven't seen them, they're on the talk list. Here I have included one of those taken by our own Chris Stevenson. Here indicated, I don't know if you can see it, but with the little pointers is where the supernova is. I think this is M62 or 61. 61. So that's that. Meteor showers, there is nothing on the go for the next month. Deep sky objects, we do have the 10 best placed telescopic and binocular objects for the next 2 months. We're still kind of a galaxy season, so the Virgo cluster and all that fun stuff, very well positioned. International Space Station, quite a few passes over the next 10 days or so, all in the evening. Then it kind of becomes quiet into June before they resume late June again. Observing sessions are not happening due to you know what. These are the observing calendars, just for, I guess, reference for the moon phase and when the monthly meeting is. So this will be June, and our monthly meeting likely going to be on the 17th. So that's all I have. Are there any questions?
No questions so far, except Dave just answered a question from Mark about possible gatherings over the summer. And I think Dave, the answer was no on that so far.
Yes.
Yeah, for the Terra Nova Star Party in particular, it would depend on if Terra Nova National Park actually opens up and would allow us to have access to the group camping fields. So that's certainly not clear at this point, even if things do continue to work to go well with the severity level decreasing in the province. But I think for public engaging type events like the Night Sky Celebration or other public outreach, I think that's probably unlikely for the summer, just because of the nature of having large numbers of people sharing common equipment in a closed or in a close environment.
Nikolai, I have a question. When would we be able to see the sky train of satellites in the near future? Is that in our list of overhead sightings?
That website, that's Heavens Above, that's listed. I believe it has that. So it's heavensabove.com. I believe you should be able to find that there.
There is also another site dedicated to the chain, and when it's coming over you by your own location, you'll have to look for that. I'm not sure if it's Spot Starlink or Trace Starlink or something like that. And if you're going to Heavens Above, for Heavens Above, put the dash between heavens and above, otherwise you'll get a surprise.
Not a heavenly one either. Okay, let's go to members' photos. One of our newer members who's going to give a talk on his telescope observatory that he built, and he sent some pictures in. I thought he would be on tonight, but I guess he didn't get on. It's Bernard Day. He has a LX200 12-inch telescope using a Pentax KD SLR camera in RAW format. ISO is 1600, 100 of a second, and this is his picture of the moon. Okay. This is another one he took with his telescope, 10 to 30 seconds of the double cluster. He says did some leveling and curve adjustments and minor adjustments in Photoshop. Okay, I don't know why I can't. I guess I'll have to do it this way. You guys seen this in color, by the way? Can I get a thumbs up from the panel?
Yes,
In
we can.
color, yes.
Okay, good. I was afraid. This is his one of the Eagle 10 30-second exposures with ISO 1600. He looked at them. I looked at them in Photoshop, Bridge, looking for defects. 7 or 8 exposures thing. It was stacked them using DSS, Deep Sky Stacker, I presume that is, using 10 dark frames. Took on the same night and the same exposure, ISO 1600, I think he was using at all times. Then some leveling and curve adjustments, and then some minor adjustments in Photoshop. Actually, very nice picture, not bad for, this is, by the way, he doesn't have his on an equatorial mount yet. These are alt-azimuth pictures. Interesting. Okay. Chris isn't here with us tonight. He's celebrating with Phil on another webinar. Phil, I remember Dr. Phil. Can't remember now. Jeez, oh God.
Phil McCausland, birthday.
Thank you. I only know him 40 years. Yeah, he's turned 50 today. So happy birthday. So this is Chris's picture of NGC 5600, 3 5-minute subs, nice bright guide star. Okay, to do the light shed using a light shield because these neighbors. Okay, oh, I know what happened here. All right, let's go on. This is Chris's photo of the straight wall. 1/500th of a second. Using his camera GIP to sharpen up curves. Okay. Oh, sorry here. Then we got Randy. You want to talk about that, Randy?
No, it's there on the screen.
Okay. Randy was out and caught the elusive X, V, and L's during as the Earth sunshine or sunrise on the moon. You actually see these little craters, and they look like the letter X. Like this one up here looks like the letter V, letter X, and the letter L. Nice job, Randy. Dave, you want to talk about this one? Okay. Yeah, this one.
So I have a visitor here.
I have a dog, I noticed.
Yeah, no, it's this supernova 2020 FQV in NGC 4568, which is one of the Siamese twin galaxies. And I think it might say there it was discovered on March 31st and is considered a type 2b, as best as I can do in the research that I've seen. I think that's still a bit preliminary. So yeah, so it's anyhow, that type of supernova tends to hang around for a while. So luckily, gave me a chance to capture an image of it.
Okay, I think this is another one of yours. M101.
I don't think that's mine.
Yeah.
From
Dave?
when?
I think it was at one of the, what do you call them? Virtual hangouts.
Oh, from
Fair
March,
party.
middle of
Yeah.
March. Yes.
It
Okay.
was,
Yeah.
12 2-minute exposures.
Yes. Right. Yeah, I'd kind of forgotten about that. Yeah, that was. It's been kind of fun for people that might be interested. The next time we do one, that we just, if we have a clear night, we get the scope up in the observatory opened up and take requests from people for targets. And of course, that was in early to mid March or middle of March. So it's right in the middle of galaxy season. So M101 seemed like a good target to go for.
Okay. Thank you, Dave. All right. Yeah. Okay. Are you there, Jim? No, that's Jerry. Yeah. Shoot.
I am.
Oh, okay. You want to
Can you
talk
hear me?
about your image? I can hear you. Want to talk about your image?
Yeah, sure. So this one here is the lobster claw and the bubble nebula. This one I shot on the 21st of April with the Explorer Scientific, the Skywatcher ED80 and ASI 1600 mm cool camera. It's a narrowband image, HA, oxygen, and sulfur. And that's about it, I guess. I don't have the total integration time on this one, but it's probably in the vicinity of 5 or 6 hours.
Okay. Let's try this one.
This one here is the crescent and some of the Saturn region, which has a lot of HA nebulosity present. Again, similar setup. I guess the only difference with this one is this one I actually captured while I was at work a couple of weeks ago via remote.
Oh, wow. All right. How about this one? Oh, wow.
And that one there is just a straight hydrogen alpha image of the Pelican Nebula. I think I did that one when I was home last time. That would have been the 25th of April.
Ooh. Pac-Man.
That's the Pac-Man Nebula, and again, it's in hydrogen alpha, or sorry, SHO palette.
Can you explain HLO palette to the members?
Oh yeah, sure. So if you think of like an RGB image, so red, green, and blue, when you capture your different subs in hydrogen alpha, oxygen, and sulfur, you basically, when you're doing your post-processing, you assign each one of those to a color channel. So the SHO palette is where you assign sulfur to red, hydrogen to green, and oxygen to blue. So it's what they call a false color, because you can't actually see any of those wavelengths of light.
Okay, and I think this is your last one.
Yep.
Ooh,
that one
wow.
there. And that one there is the
Fish.
fish head and part of the upper part of the Heart Nebula. And again, that one I captured when I was offshore. I think just the first one I returned this hitch. So it was another remote image that I captured. And I think this one was probably on the magnitude of 8 or 9 hours of exposure.
Wow. So you're doing this remote like 200, 300 kilometers away?
Well, I work on Hibernia, and my telescope is in my backyard in Foxtrap. So.
Wow. Really good. Okay, thanks, Jim, for
Well, thank you very
sharing.
much.
Okay, this is mine of the Alpine Valley here of the moon, taken a couple of weeks ago now. 30 frames, no Photoshop done, just a simple pose. And this is Venus. Let's see if I can get this. I can't. It's supposed to go through phases, but because let's see. Oh, every time I try to get something here now. Okay. Slideshow. Okay. Let's see here now. No. Hmm. Hmm. How come? Okay. Yeah. I just thought I'd let you see my light pollution from my house since my neighbor has put up a light. These are both taken with the same camera, same position, same exposure, 1/8 of a second. On your right, this is when the light's off. This is how dark my backyard is. And this is how bright my house is when the neighbor turns his light on. I can read in my bedroom now. Impressive here. Okay, I'm going to just whiz right through here. Oh, shoot. Okay. Okay. There you go, the little gift. I've been doing Venus in white light, UV light, and infrared light. And I just want to, I put them all the white light ones together just to show you as it goes through the different phases. Kind of cute. Haven't had any clear skies. And for my house now, it's down below. It's blocked by the neighbor's new barn, baby barn. That's it. Okay. Any other things to be brought up before we end the meeting? I want to thank everybody who did pictures. I want to thank our speaker tonight. I thanked her, but I'd like to thank her again. I thought the section on Pluto was really good. I hadn't seen that detail of information on Pluto and with the rocks and the water flows and the ice things, and noticing that ice floats in a nitrogen ocean. Interesting.
There's some pretty nice detailed photos with that Pluto bit as well.
Oh yeah, I've been looking at a lot of them, but usually they show the pictures, but they haven't sent out any analysis with them.
What's that background of yours, Dave?
It's the Elephant Trunk Nebula and region.
That'll make a nice submission for the newsletter.
I'll send it to you if you like.
Anyway, any messages on chat or any questions? So we'll see you all on June the 17th for the next meeting with Bernard Day, talking about the Dome on the Hill and how we built it from scratch. During the month, join the RASCNL talk by leaving a message at info@stjohnsrasc.ca. So you can join. You'll meet guys who will gladly let you decide what to watch on your telescopes. There's actually been, I think, 3 or 4 workshops given on how to use Photoshop, Pin Insight, DSS, Astro Toaster. So if you're into any of these things, maybe someone wants to hear about how to do something visual for a change. I don't know. Anyway, that's it. I hope you all enjoyed yourselves, and thanks for coming, and see you on June the 17th. Keep looking up. Keep safe. Thank you very much.
Good night, everybody.
All right.
Good night. Thanks, Gary.
Okay.